starts with, let's say, AB, okay, this pattern. Example, I think example number, let's say example 1, 2, 3, example 4. Okay, starts with AB. Okay, so now again table A and B. Okay, and now see how the thinkings are being applied in this case. QS on input A. So my first alphabet is A. Okay, first alphabet is A, and again remember in QA. When B comes, when B comes, now this pattern says that A and B, and first alphabet is A. First alphabet cannot be B. Okay, your string can never begin with B. Previous it was different situation, but here in this case it is saying starts with AB. Okay, so your first two alphabet is very restricted in this case. AB, A, AB, B, AB, double A, and so on. Okay, and so on. So this is the string that we are going to accept, and first alphabet cannot be B. So what we have to do in this case is we have to, because it's not allowed. Okay, not allowed. Okay, it is not allowed. What you have to do is you have to reject it. Okay, so why I am rejecting it in this particular case? Because the first alphabet cannot be B. Previously it is allowed, first alphabet can be B, no restriction, but here it is restricted. Now QA on input A, second alphabet is also restricted. The first alphabet cannot be A, B, second alphabet cannot be A. So again it is not allowed. So what we need to do in this case is reject it. Okay, reject it. Reject state, dead state, or trap state. QAB, fine. QAB, first and two alphabet restricted. Okay, so when I write this this small let's say 4 or 5 string, you understand that none of it, okay, none of it contain any other symbol than A and B. So not allowed case. Now QAB, once it is satisfy the condition. So AB is already there. Okay, anything you write over here will be accepted. Okay, AB, after AB you can write anything. Okay, so for example, if the first alphabet is AB, later part is a 2-length string, I can write double A, I can write AB, BA, AB, AB, I can write AB, BA, or I can write AB, BB. Okay, ABB, I can write anything in this case. Okay, so QAB and QAB. Okay, R. So this is the first time it's been introduced, that is called a reject state. Okay, and reject state is basically R is a reject state. Okay, reject state or a dead state. Okay, reject state or dead state. So I required here, why I required reject state? Because this condition is going for not allowed case. Okay, this is not allowed. Okay, so it is not allowed, and that's why we are rejecting it. Now diagram, if you have done with diagram, it's totally fine with me, it's okay. So QA, okay, B is not allowed, B is not allowed, QA, double A is not allowed, AB, QAB, everything is allowed in this case. Okay, so A and B, and this is the final state. Okay, so this is all string that begins with AB. Okay, and this is the diagram. Sorry, this is Q. Okay, Q R. It's a R. Now, when you say minimal number of state, okay, when you say minimal number of state, okay, it will be 4 in this case. Okay, let's not talk about minimal number of state. Okay, the only comment I will right now make is we need to count. Okay, if the question is whether we need to count R or not, reject state, we need to count reject state. Okay, we need to count reject state in this case. Okay, so whenever later we will talk about more in terms of formally in terms of optimization, in that case we need to count the reject state. One question you might be wondering that why not in QS. Okay, why in previous case we are using QS but not here? Because in this case reject state. Okay, now reject state, it is not allowed. If B is simply the first alphabet can be B in any of the string, we will consume it. But the problem is that none of the string will contain the first alphabet as B. Okay, and that is why it is not allowed. And when it is not allowed, we'll send it to reject state. okay, and reject state have a property this A and B. Okay, so this is the pattern. Starts with AB, quickly complete, starts with whatever you like, starts with double B. Okay, let's complete starts with double B, and just complete this one, complete the table, starts with double B, the second type of the pattern. This is example number 5. Starts with double B. Okay, few string that we can write: double B, BBA, BBB, BB double A, BBAB, BBBA, BBBB. So again, if you look at any string over here, you will not find the first two alphabet as other than B and B. Okay, so you will not find any other string than B and B. So what we need to do in this case is we have to we are, what is not allowed? The first alphabet A is not allowed, second alphabet A is not allowed, and once we come to this not allowed case, then we have to create in this case a reject state. Okay, so that is the idea of a reject state in this, and start pattern contain the reject state table QS A and B. Okay, A and B, and what is not allowed? A is not allowed, reject it, remember it. QB, second alphabet, again A is not allowed, reject it. Double B, remember it. Q double B, everything is allowed, so Q double B, Q double B, and R, this behavior is important. Final state, starting state. Okay, so QS A, R, B, QB, again one more time A, R, one more time A, Q double B, so two B's are occurred. Final state, and you see all the example string. After, once you have two B's, two A's are not allowed, everything else is accepted, either A or B, right? So that is the idea. Okay, starts with the double B, this is the language, and this is the table, and this is the diagram for it. Okay, it's up to you. Okay, once you start feeling comfortable, then directly go and draw the diagram. Okay, but here you can keep track whether it is DFA, particularly you're designing the machine as a DFA or not. No multiple entry, and all places no blank space. Okay, no blank space, DFA. Okay. Okay, now so we have done the starting pattern and ending pattern. Okay, so let's have one method. So okay, fine. Example number 6. Okay, example 6, and this will be a bit lengthy example. In this case, we'll work on something else in this. We have worked on one method, that was the transformation method, and we'll work on a bit different method in this case. Okay, so let's go with this. All string. Okay, example number 6. All string over A and B. Okay, starts with A and ends with B. Okay, so in this particular case, we want to learn a new method in this case, and in this particular case what we are learning is we have two separate languages. Okay, so we have two separate two parts are there. Okay, so one part of this is starts with A. Okay, all string starts with A. Okay, and another part is all string, okay, ends with B. Okay, so let's go with our usual method and design it, then I'll come to the alternative perspective. Okay, so so now we have seen already the starting pattern, we have already seen the ending pattern, both pattern we have already seen. Starts with A and all string ends with B. What we want here in this case is we want this AND operation in this case. Okay, AND operation in this case. So this is your AND operation, and I already told you that AND operation is equal to your intersection. Okay, I'm not commenting anything, but this particular string starts with A and ends with B. Okay, so language is a very good practice that you write few string for this particular language. Okay, epsilon does not qualify, starts with A, ends with B. So starting will be strictly A and ending will be strictly B. So AB. Okay, starts with A and ends with B. So A and B, the middle part can be A, the middle part can be A, B, B. Okay, this language starting is A, ending with B, the middle part can be anything, double A, AB, BAB, or ABBB. Okay, anything, but starting will be strictly alphabet will be A, and starting will the ending alphabet will be B, ends with B. But starting, you see, again there is a that in all the string that I have written, the beginning is not allowed with B. Okay, all the alphabet consists of the first symbol as A. Okay, so now okay, so QS, A and B. Okay, so so now A is allowed. Okay, with the previous example A is allowed, and I'll remember QA, fine, I'll do it. But as I told you that all the string that I have written is not begin with B, none of the string begin with B, so QS on input B will be rejected. Okay, so B is not allowed. As you can see that none of the string whatever I have written is having the first symbol as B, so reject it. Okay, now QA, now behavior of QA. Now A is the first to work on, that the last symbol must be B. The first alphabet is A. Okay, second alphabet can be A, double A, fine, it's okay, there are few string, double A is there. Okay, double A is there, so A followed by more number of A's. Okay, so last scan alphabet is A. That is the idea. You started with A and more A's are coming. So last scan alphabet, double A, triple A, 4 times A, every occurrences of A, the last scan alphabet is A only. Okay, so this is the idea. So we'll not go anywhere, we'll remain into QA. Okay, the moment B will come after A, or after A directly B will come, after A directly B will come, or double A after that B will come, all are valid string, right? All are becomes a valid string. So after A, when B will come, we'll go to QAB. When you are in QAB, you are perfectly in a state where starting symbol is A and ending symbol is B. Now we need to define the behavior QAB. Okay, QAB. Now you feel this, that starting pattern satisfied, anything comes it will be accepted, but in ending pattern it is not true. Okay, in ending pattern after AB more symbol can come, like here you have successfully double A and B, you successfully ending with AB, but more symbol can come, let's say AB, this is also a valid string. Okay, so more symbol can come in ending pattern after satisfying the condition, more pattern, more string can come, and it can later also satisfy the condition. So QAB I have to define. So there are two possibilities are there after QAB. Okay, if either A will come, okay, or B will come. Okay, there are only two possibilities are there. Okay, and if after A will come, so you cannot end the any string. Suppose A, B already satisfied A, you cannot end the string with A, right? You cannot end the string with A. So after AB, if more A's are coming, then we will send it back to a QA state, that the last can alphabet is B. But if again if there is a B already there and more B's are coming, 1B, 2B, 3B, 4B's are coming, when more B's are coming, then the last can alphabet remain as B, and we are still there in the satisfying the condition. Okay, so in this case, if it is there, then I am totally okay with this, and more B's we can consume in Q, A, B, R, R, R. Okay, so first of all, it's an intersection of two languages. This is the few example string, and this is the table for it. Okay, table for it. Okay, so if you have done, you got it correct, and if you have designed the diagram for it, look at match your diagram. QS on input A, remember in the state QA. Okay, B is not allowed, any of the string is not allowed, so reject it. Okay, reject it. And if more A's are coming in this case, then we will consume it here. More A's are allowed, there is no restriction on the second alphabet. When B will come, it will become a valid string QAB, and you reach to the final state. Okay, you reach to the final state, and in this case, if A's are coming, then we'll go back to the state that remember A's. If B's are coming, then QB's. Okay, so this is how the diagram will look like, and this is a perfect DFA, a 4-state solution. Okay, a 4-state solution. Okay. Okay, so this is a DFA, starts with A, ends with B. It's a directly I have designed this method. Okay, and A and B. Okay, so I hope it's okay with you. Okay, let's conclude, or let's define a method by which we can say that this 4-state is this DFA is the minimal DFA. Okay, is this a minimal DFA? This is the question. Is it the optimized one? Is this a minimal DFA? Okay, so this is the question. Is I want this verification, that is this DFA 4-state solution, can I do it in a smaller number of state? Okay, so basically, is this a minimal DFA? Because we have done, let's say, quite 5-6 questions we have already done. Now we can address this issue, that is this DFA, deterministic finite automata, is a minimal one or not? Okay, so now we have to learn a method for optimization, minimal DFA, to check whether it is minimal or not. Minimal means a 4-state solution is there. Is it the minimal one? Can I do it in 3, 2 or 1? Okay, is it possible? So that way, minimal DFA. So now we'll talk about a method that verifies us the situation that whatever we have designed is really consists of minimal number of states. We'll take up the same example. Okay, but let's learn this method that can say that my DFA is really consists of minimal number of state. Okay, so DFA or minimization. Okay, DFA minimization, and this method is called partition method. Okay. So, so there are few things are there that is very trivial. There are two partitions are trivial. Okay, two partitions are trivial. We can say equivalent and non-equivalent states. Okay, so the two partition, the first partition and the second partition is trivial partition. Okay, so there are both partitions you can apply on any DFA. Trivial partition. Okay, so the first partition is partition the states into final and non-final states. Okay, I will take up an example. Okay, let me just write down this few methods for this, and then I'll take an example. So partition the entire states into partition the states into final and non-final states. So one partition will consist of entire final state, and another partition will consist of entire non-final state. So partition them into two different states. Okay, now for each partition, for each partition final and non-final state, further partition them based on following behavior. Okay, so based on the following behavior, again you make the partition. So now this example I am giving you for two alphabet. Okay, sigma is equal to a 2 alphabet. If there are 3 alphabet, then there are more combinations are possible. So first partition was final and non-final state. Second partition was that each partition means final differently and non-final differently. Each partition you further partition them based on the following behavior. Okay, so now this is A and B. Okay, and this what you do for final state you do, and for non-final state you do the same thing. So this you will do for non-final state, non-final partition. And this you will also do for final partition, A and B. This is your final partition. Okay, so there are two different types of the partitions are there, final partition and non-final partition, and they can behave in only in this way. Okay, so either both inputs are going for a non-final state, non-final, non-final, final, non-final, non-final, final, and final. Meaning is that you examine your states. Okay, examine the states and examine which partition, examine the non-final partition in this behavior, whether both of these partitions are going for the non-final state, that is one partition. Okay, this is one behavior. The second behavior is on A they are going into the final state, on B they are going into final state, and A non-final state, or both the input they are going into a final state. So the behavior on input A and B, because 4 combinations are possible. If there are 3 alphabets, then there are more combinations are possible. Generally 2 alphabets type of the questions are there in the examination. So let's focus on this part. Non-final and non-final, 3 also we can address. Both non-final, on A final, B non-final, A non-final, B final, both are final, non-final state. Same behavior for final partition, that both are non-final, final, non-final, non-final, final, and both are going into a final state. Okay, so this is the 2 trivial partition. After that, the next step I'll tell you, let's do examples of for this 2 trivial partition, and then we finally progress the third step. Okay, so this is the first 2 trivial partition. Let's have a example of doing this, and then we'll make the further progress, that how we can check further they are equivalent or not. Okay, so this is first 2 method. We'll practice first 2 method, then I'll say the third method of the partition. Okay, so this is trivial, you can apply anywhere. So suppose this is the diagram that is given to you on alphabet A and B. Okay, a bit of big diagram in this case. Okay, so this is your DFA. Okay, let me just 0 1 B on input 0 is going for the state G, and 1 is C, 0 and C is 1. This is 0 and 1. Okay, 0 and 1. E on input 0 going to the state H and E on input 1 going to the state F. Fine. F on input 0 going to the state C, F on input 1 G, G on 0 and G on input 1, and H 0 here and 1 here. Fine. So this is a table for it. Zero and 1. Okay. So A 0 on input 1 F, B0 is going to the state G, B1 going to the state C, C on input 0 going to the state A, C on input 1 repeating, okay, D on input 0 going to the state C, D on input 1 going to the state G, E on input 0 is going to the state H, E on input 1 going to the state F, F on input 0 going to the state C, F on input 1 going to the state G, G on input 0 going to the state itself, G on input 1 going to the state E, H on input 0 G, and H on input 1 going to the state C. Okay, so starting state and final state. Okay, so this is the big FSM, finite DFA, and we want to minimize and we want to see whether it is the minimized diagram, minimized DFA or not. Okay, okay, so partition method says that you first perform the partition based on final and the non-final state. So this is the outcome of the first state. Okay, this is the first step and this is the outcome of the first state. That in this case only C is the final state and rest of them is a non-final state. Okay, only C is the non-final state, final state, and rest of them is a non-final state. Again, if you look at the diagram, okay, there are few cases in which, in this case again, table will be helpful for you, because you can clearly see, rather than going one by one to the state, you can directly look at the table and you can find out the partition by yourself. Okay, so in this case your first partition is a non-final state. A, B, D, E, F, G, H all are non-final, and C is and final state is consist of only one partition. Okay, so this is non-final and another one is final. So non-final and final. Okay, non-final and final. Okay, so this is the non-final state and final state. Now what you can do here in this case is again we can further divide. Now this is the first trivial partition. Second trivial partition is each of them you can further divide in different ways. Here no possibilities are there. There is a single partition. So in the next step I will write here C only. But A, B, D, E, F, G, H I can analyze and I can make the partition based on their behavior. Okay, so let's see where is my final states are there, except C, because C is already been separated. So if you look at C, on input 0 C is available here and here. Okay, on input 0 C is available here, and on input 1 like D is on input 0 C, and on input 1 G non-final state, F on input 1 also going to the state G. So these two category D and F is the category on input 0 final, on input 1 non-final. Okay, D and F are the category on input 0 final state, on input 1 non-final state. Again you find C in the one column. Okay, so this is the place where C is there and this is the place where C is there, B and H. Okay, and on input 0 both are G and G. So what is this category? This category is on input 0 non-final, 1 final, 0 non-final, 1 final. Okay, so this is on input 0 final, this is on input 1 final. What we remain with? A, B and F both are non-final, E, H and F both are non-final, and we are left with G, G and E both are non-final state. Okay, so as I told you that there are only 4 different possibilities are there, that on input 0 and 1 Okay, more possibility we can write down non-final, which is your A, E and G. On input 0 final and non-final, which is your on input 0 final state, which is your D and F. On input non-final and final, which is your B and H, B comma H, and both are final. We don't have anything over here. Okay, so we don't have any partition for this one. So now this thing can be divided into 3 different partition based on this behavior: A, E, G, okay, and D and F. You can say the category, what category they belong. Okay, so non-final, this one is final and non-final, and this one is non-final and final, and in this case B and H. And already we have a partition consist of, see, brackets. I changed the bracket, but it is okay. Let's have the consistency. Okay. Okay. So this is the 2 trivial method. First is final, non-final. Then based on this behavior, you further partition them, and it's only one step. So the 2 step you have already come across to 4 different partition. Okay. Now, okay. Now the third step. Okay. The third step. Okay. So third step is this, that two states are equivalent or belongs to same partition. Okay, if on the same input, they reach to same partition. Okay, so now we don't need to think in terms of states, we have to think in terms of partition, that A and E, like 2 states, are equivalent if on the same input they are behaving same, means they reach to the same partition. Okay, so now how to check, how to verify? So suppose I want to check A and E, I want to comment whether A and E are equivalent or not. Okay, so I will see the behavior. A on input 0 going to the state B, so B, and E on input 0 going to the state H, that means H. Now in this case you observe B and H belongs to the same partition. So A and E on input 0 going into the same partition, though different state, but both of the state belongs to the same partition. So A and E on input 0 behaves same. Okay, same behavior, behaves same behavior. On input 1, let's see, A and E on input 1. So A on input 1 going to the state F, and E on input 1 also going to the state F. Now what we can say, same behavior in this case also. Okay, so they are, A and E are not separate state, they are equivalent. Okay, again I am repeating, it is not about the same state, it is about the same partition. So one A and E, B and H, but B and H belong to the same partition, to same behavior, and on input 1 they are same. Now one of them I will check with G, whether G belong to the same partition. Let's check A and G, or E and G, whatever you can check, because A and E are equivalent. So A and G. Okay, so A and G, A on input 0 going to the state B, and G on input 0 going to the state G, means the situation is that this is going to 0 and this is making a self loop. I need only one behavior to say they are not equivalent. Okay, and this 0 behavior is saying this thing, that they are not equivalent. Okay, so what is the idea in this case? That A and G are not equivalent, and if they are not equivalent, then what we can do, we can separate them. Okay, so we can separate them as A, E and G as a separate partition. Why? A and E behaving same and E is behaving differently. Now in this state D and F, okay, in this state D and F. So D and F in this case CG and F is also CG. So there is no question of separating them. B and H, okay, B and H, B and H, G and C. So there is no question of separating it. So this is not getting separated, D, B and H not getting separated, D and F not getting separated, and this is C. Okay, so in this particular case we are not separating them, and this is the partition. Now what you need to do is final time, one time you check this behavior that A and E, okay, are in the same partition. So on input 0 both are going to B and H, and E B and H, and on input 1 both are going to the state F. G is making a self loop, G is making a self loop, G and E self loop and going to the state C. B and H DF already verified. Okay, okay, so the process will stop. Okay, process will stop. Okay, if no partition, okay, if no partitions are possible, process stops. Okay, so if no further partition can be done, then this process will stop. One more step is there, fifth step. Now it may be possible that like in this particular case you can do it at the beginning also, at the end also you can verify this situation, that in the beginning, like here if you examine D, okay, so D is an unreachable state. Okay, D is unreachable state. Okay, so D is a unreachable state, and if some state is unreachable, then you can remove it. Either you do it in the beginning, but the only thing I want to make sure here in this case, that if it is having common behavior, then it will combine with some of the reachable state, like D is combined with F. Okay, so if it is having some common behavior, it will combine with it. If like here in this case it is combining with F, F is reachable, fine, so any unreachable state is combining with this reachable state. Okay, but the last step is if any unreachable state, okay, any unreachable state can be removed. Okay, so it is not a restricted on that you have to remove at the beginning or you have to remove at the end. The only thing is this process is so good that even if it is not removed earlier, it will combine with one of them. Okay, so don't worry about this. You can check it beginning also, and you can check it at the end also, that if the state is unreachable, can remove it. Okay, so I think the first two steps are very much trivial, that final and non-final, and then when you further dividing them into the different or separate partition, okay, then final, non-final, then behavior, 4 different behavior for 2 state solution, and then I need to check one time whether on input 2 states are equivalent if they are going into a same partition, not the state, remember it, not the state, same partition. Okay, so this is the partition method, and you can verify each of them. Okay, each DFA whether it consists of minimum number of state or not. Okay. So let's see whether whatever we have designed for ends with, or you can go, I will complete that problem. By that time you can verify whether example number 6 that was begin with A and ends with B is consist of minimum number of state or not. Okay, so this is your problem. Just complete it now, that whether the problem example number 6 consists of minimum number of state or not. Okay, by that time I'll just complete this one. You just verify whether begins with A and ends with B, that diagram is consist of, the DFA consists of minimum number of state or not. Okay, so example number 6 was this. Okay, so I want to verify whether I am having the state as a 4-state solution is minimal or not. Okay, so this 4-state solution, okay, is it minimal? Okay, is it minimal DFA? Okay, so even if you have done it correctly, and if you have done this in a minimum, let's say more number of state, we can verify this situation. Okay, so let's have our first step. What is the first step? That all non-final in one state, QS, QA and R in one state, okay, and all the final state in a single state, QB. Okay, so fine, we are done with this. Now we have to apply the second method, which is also trivial one, and because we have an input A and B, just write down that A and B behavior can be what? It can be your non-final final, non-final non-final, final non-final, non-final final, and final and final. Okay, so QS. Achha, now what happens in this case is that you have to verify each time. Okay, table give you this slight edge over this diagram for this partition method, that you can verify by looking at the table the states where it is reaching. So on input A and B, both are QA and QR. QA and QR both are non-final state. Okay, so this QS qualifies for this situation. Okay, QS QS and QR. Okay, first symbol B. A, B not allowed. A starts with, okay, fine. Achha, QA. QA is QA on input A final, on input A non-final, on input B final. So QA here. Okay. QS QR. Okay. QS QR, and QR is also on both input R, so that is final only. Okay, so now first thing is that we don't have to partition, because there is a single non-final state. We don't need to partition QB, but these are going further partition into two parts, QS, QR and QA, because QS and QR on input A and B both are reaching into non-final state, and QA on input B reaching into a final state. Okay, on input B it is reaching to a final state. So now this further partition can be done as QS, QA, okay, QS, QA, QS, QR in a single state, and there will be a QA and there will be a QB. So once I have done this trivial two thing, then I need to verify whether the two states are equivalent or not, whether QS and Q are equivalent or not, and this I verify based on the situation whether they are going into a same partition or not. Okay, so whether QS and Q are going to a same partition. Okay, so QS on input A is going to QA, but QR on input A is making a self loop. So the behavior looks like this. Then the moment, you don't need to verify everything, that A is here and this one A is here, like this. If it is same, means both are A, then okay, but in this case then I'll check QB on B, but in this case one is going into a this partition and one is making a self loop. That means QS and QR cannot be in the same partition. So in the third partition will come, QS, QR, QA and QB all are separated. Okay, all are separated, and in this case we started with 4 state minimals. 4 state is a minimal solution. If it is not minimal, then I'll get, let's say, 3 partition or 2 partition, but in this particular case this is the minimal DFA, accepting starts with A, ends with B. Okay, starts with A, ends with B. So the question, is it the minimal DFA? Answer is yes, this one is the minimal DFA. Okay, so this is the example we started with, and fine. Let's check one more example for minimal condition. Okay, let's say example 7, minimize the following DFA. So drawing the table, QS 01, 15, Q1 62, Q2 02, Q3 26, Q4 75, okay, let's check this one whether it is the minimal one or not, minimal DFA or not. So start state is Q0, okay, and final state is your Q2, okay. So this is the minimal DFA or not. So let's say 1562 02, okay, 2675 26 64 and 62. Okay, let's check this one. Okay, so only one final state and rest of them is non-final state. So again, just step 1, step 2 is the two trivial one. Okay, so in this partition Q0, Q1, Q2 you skip, Q3, Q4, Q5, Q6 and Q7. Okay, so there are 8 states are there, 7 belongs here and Q2 belongs here. Okay, so this. Now what you can do directly, what you can say that you can directly have 4 different partitions from this with behavior on A and B as non-final, non-final, final, non-final on A and B, non-final, final and both final. Okay, and why table helps all in this case, because again Q2 is the final state. Okay, so I can circle Q2 wherever Q2 is present and I can accept the final because I do not club the final one, Q2. Okay, so this is how you can go with this, that Q2 are final state, and I skip this one because this is already partition 1. Okay, so now on input 1 final, if you say if on input 1 final, so on input 1 final is your 1 final is this Q1 is on input 1 going to final, non-final, and Q7 on input 1 0 non-final and 1 final. Okay, so 0 on input 1 final. Okay, so okay, A and B, so 0 1 0 1 0 1 and 0 1. Okay, so on input 1 final state. Okay, this partition, and here in this case I can put Q1 and Q7, right, on input 1 final. So this is Q3 and Q5. Okay, Q3 and Q5. So I can put this thing Q3 and Q5 in this partition, final and non-final. Q3 on input 0 2 2 final, final. Okay, non-final. Rest of them is non-final because we don't have a final. So what we are left here in this case is we are left with Q0. Okay, we are left with Q0. We are left with Q4. We are left with Q4 and we are left with Q6. Q6. And this is Q2. Okay. Okay, the next method is individual partition. So I will analyze everything Q3 Q5, like let's say Q3 Q5. So Q3 Q5 3 and 5, Q2 same behavior, Q6 Q6. So the moment this is Q6 and Q6, you don't need to check because they are already have the same behavior. 1 and 7, so 6 2 and 6 2 already no further partition possible. 0 4. So 1 is Q1. So this is your Q1, on input 0 it is Q1 and 4 is going for Q7. So 0 is for Q1 and Q7. Q1, Q7 are combined behavior. So I cannot differentiate between 0 and 4 based on the behavior of 0. On input 1, Q0 and Q4. So on input 1 Q5 and Q4 is on input 1 is also Q5. Same behavior. Let's check one of them with Q6. So Q0 check with, let's say, check with Q6. One of them will check with Q6. So Q0 and Q6. Q0 on input 0, Q1. This partition Q6 on input 1, Q6, making a self loop in this particular case. Okay, so I cannot have this thing in the same partition. So what we can do here in this is we can go with Q0 and Q4, and Q6 can be separated. Okay, Q3, Q5, Q1, Q7, Q2. Okay, no more further partition can be made, it can be done over here, and this is my final result. Okay, so this is the partition method. Doubts? Okay, so we'll stop here. Okay, in this case,